So, good morning to one and all present here. I'm Kashish Vishwakarma from Prestige Institute of Management and Research. I'm a BTech CIC first year student, and today I'm here for the presentation on the topic Lagrange's mean value theorem. So, let's start my presentation. So, I welcome everyone to my presentation. So here is the learning outcome. So by the end of this presentation, you would be able to understand the concept of Lagrange's mean value theorem, the statements and its proofs, and also you will be able to understand the real life application that where is the Lagrange's mean value theorem is used. Okay. So now here is the outline. So first we are gonna see the Lagrange's mean value theorem, then the geometric interpretation, then its statement, then proof, then examples, application, and then conclusion. Okay, so Lagrange's mean value theorem. So here is the essence. So let's understand about what is the essence of this. So the essence is generally in calculus, the mean value theorem states that for a continuous differentiable function, there at least one point where the instantaneous rate of change is also termed as derivative. Okay, so it is equal to the average rate of change over a given interval. Okay, if you do not get understand by this, so you have to first visualize it. So here I'm having a good example for you so that you will be able to imagine it. So now you have to imagine a car. Okay, so a car is traveling on a highway. The mean value theorem states that at some point the car must have reached a speed equal to the average speed over the entire trip. So let us imagine first. Okay, so if your speed, okay, so it is like 100 kilometer per hour. Let's assume it like this. Okay, so now the 100 kilometer per hour speed is can be we can term it as the average speed. Okay, so on the highway where we drive very faster, right? So it is possible that our speed should also be reached to 100, also maybe it reached to 200 as well, right? So here it's said that it is the average. Okay, so it may be equal to the average speed of the entire trip. So it means like, okay, so now let's comes to the geometric interpretation. So here we are having secant line, tangent line, and mean value. Okay, so secant line, the line connecting the endpoints of the interval representing the average rate of change. Okay, and the tangent line is the line touching the curve at the specific point, representing the instantaneous rate of change, okay, of that point. Now the mean value, that is the point where the tangent line is parallel to the secant line, representing the point where the instantaneous rate of change, okay, is equal to the average rate of change. So it is very simple. Okay. Okay, so after understanding the geometric interpretation, okay, and the essence and visualizing it, what is exactly the mean value theorem or the Lagrange's mean value theorem? Okay, so let us understand that. Okay, so here is a graph, or you can see over here. So here we are having this function, and here is the tangent passing through that point, and also the secant line. So here is the A, B, and C intervals. Then it is f of b minus f of a upon b minus a. Okay. Now the statement of the mean value theorem, it is having the conditions, that is a function must be a continuous on the interval, closed interval, that is a comma b, and it's differentiable on the open interval a comma b. Now guarantee there exists at least one point c in the open interval a comma b where the derivative of the function at c is equals the slope of the secant connecting f of a and f of b. Okay, so this you would be able to understand simple points. So here is over the summary, overall the summary, what I have told you before in the previous slide, right? So the Lagrange's mean value theorem is exactly what is it? It is the exact version of it. Here it's explained in a very simple language. Here it is the Lagrange's mean value theorem. So let f of x be a real valued function defined in the interval a comma b such that f of x is continuous. Okay, so here f of x should be continuous in the closed interval of a comma b. It should be differentiable in the open interval a comma b. Here functional value of a should not be equals to functional value of b. Okay, and also here we can say that then there exists a point c where c will be belong to a comma b such that we can say that f of c equals to f of b minus f of a, okay, and upon b minus a. Okay, so this is very simple topic. Okay, so now how we will prove this. Okay, so let me tell you about the proof of the topic LMVT. So here are the certain steps. Okay, so constructing a function, first you have to take a function. So you need to define a new function, that is g of x, representing the difference between the secant line of the function. You have to apply the Rolle's theorem. Okay, show that a g of x satisfies the condition of Rolle's theorem, which guarantees the existence of a point c where g derivative at point c should be equals to 0. Okay, now then you need to derive the result. Okay, so simplifying g of c and equate it to 0, resulting in the equation f dash of c is equals to f of b minus f of a upon b minus a. So now you will prove this. Okay, so here is the exactly the statement. Okay, the Lagrange's mean value theorem states that if a function f of x is continuous in the interval, in the closed interval, you need to remember this, that it is continuous in the closed interval a comma b, and it is differentiable in the open interval. Clear? Okay, such that the slope of the tangent at that point c is equal to the slope of the secant through the endpoints of that curve. So f dash of c equals to f of b minus f of a. Now the proof. So proof is, let's so as stated before, we have taken a g of x. Okay, now it is passing through and will be let g be the g of x be the secant line. So it is the secant line. Okay, then f of x, so that means it is passing through the function f of x that we have seen in the graph, right? So it is the similar one. So here we are having the points a comma f of a and b comma f of b, and also we know that the slope of the secant is m. Slope is denoted by m, then f of b minus f of a upon b minus a, and the formula for the secant is y minus y1 m into x minus x1, and the further equation is y minus f of a is equals to f of b minus f of a upon b minus a and into x minus a. So what we did is just we have written this, okay, with the secant line, and this we have written its slope here. Okay, so it's not at all difficult, it's very simple. So okay, so what is this? Here is you are having the secant line equation. Okay, and we have put the value of m here over here. Now we will solve this up, and since the equation of the secant is g of x and y, so we are having this. Now after, okay, so after here we'll so like this we are going to prove this up, and after that at the end what we'll see here, that is h of x is continuous on a comma b and is differentiable on a comma b. Okay, so here you need to, as I stated before, that continuous in closed interval and differentiable in open interval. So like this we have proved it up, and then thus applying the Rolle's theorem, there is some x equals to c in the open interval a comma b such that h dash of c equals to 0, and then h dash of x is equals to f dash of x minus f of b minus f of a upon b minus a. Now for the c, okay, so it is coming to the end for some c in h in a comma b, h dash of c is equals to 0. Thus what we can say that f dash of c, okay, minus f of b minus f of a upon b minus a is equals to 0. Then finally this will be shifted to that side, so this whole will be at positive. Okay, so finally what we proved, that f dash of c is equals to f of b minus f of a upon b minus a. Okay, so thus the Lagrange's mean value theorem is proved. Coming to the example, so here we are having the example. Okay, so you need to verify the function. So this function is given x square plus 2x minus 8 satisfy the Lagrange's mean value theorem in the interval minus 4 comma 4. Okay, so now the solution is, what you have to do first step is check the continuity of the function. So since it is a polynomial function, so therefore it is continuous. Okay, and now we'll check the differentiability. So we have differentiated it. Okay, so now it's differentiable in the open interval minus 4 comma 4. Then what we have taken? We have taken the functional value of minus 4 and functional value of 4. Okay, so it should not be equal, and yes, it is not equal. And then we have applied that, it means that three conditions satisfy. So there exists a point C, right? So the point C there, okay, is so we note the formula as we have proved before, right? So it will be f of 4 minus f of minus 4 upon 4 minus of minus 4. Okay, so here you got the value of f of c equals to 2. Okay, at the end, then you'll solve it. So so here what you will get at the end, c equals to 0 lies in the interval, open interval, that is minus 4 comma 4. So this is your answer, and therefore it also satisfies the Lagrange's mean value theorem. Okay. Now here we are having example number 2. So here we are having a different function and different interval, but the concept and the logic is exactly the same what we have studied before, right? So here is the function again, and we have checked that it is continuous or not. So yes, it is a polynomial, so it is definitely a continuous. Okay, and also it is differentiable in the interval, open interval 2 comma 5. Also we are f of 2 is not equals to f of 5. Then we have used the function, okay, functional, that is the formula, okay, at point C, and we found the point C, that is 3.5. So now our final answer is, therefore, since C belongs to C equals to 3.5 belongs to the interval, open interval 2 comma 5, the function f of x satisfies the Lagrange's mean value theorem. Okay, so here you have understood that what is the Lagrange's mean value theorem, right? And also its proof, its example, so you would be able to understand that it's very useful, right? So the applications, now where this is used, it is very important. Whenever you study the topic or the concept, you should also know the applications of it. Okay, so what is the first application here is the motion. That means understanding the velocity and acceleration in physics. So maths has a great role in the physics as well. Okay, now the optimization, finding the optimal solution for the function within a given interval, right? We used to find the optimal solution out of it. And you already know that calculus has a major part in the calculus. Okay, so calculus, that proving the calculus theorems, okay, solving the specific problems, we have a greater use of Lagrange's mean value. Okay, so after this, in the conclusion, we can say that, okay, that there exists a point in the interval such that the tangent at the point C, f of C, is parallel to the line that passes through the point A comma f of A and B comma f of B. So here you can see the graph is also there, that function what we have studied before, right, during the proof. So this is its graph. Okay, so you know that the point C, it come out to be good, right? So it was like this. So here my presentation comes to an end. I would like to thank Devendra Gautam sir for giving me the opportunity to present my PPT over here. Thank you, sir.